Well, hello there. Welcome to my channel. Uh, have you ever wondered, is there a way to calculate how much power I can get out of my solar panel today at my location, at my temperature, and with my sun level? Well, the answer is yes, and it's really not that hard. So let me get a little background information out of the way. I'm placing this information in the public domain. You can copy any part of this presentation, use it as is. I don't care. What I'm trying to do is express how to find out how much power can I actually get. Over here I have two solar panels. One is nicely in the sun, and this one, it's hard to tell, but it's actually partially shaded. I measured one of these panels by itself, open circuit, with an air temperature of 31 degrees, and I measured the panel temperature or the cell temperature to be 58 degrees C. Okay, I used this particular infrared thermometer, but I have another one I could have used, and I used, since it was open circuit, I didn't even bother measuring the open circuit voltage, which I should have, but in the rest of this presentation I'll show you how to use this to measure the short circuit current. And this is a little more expensive multimeter for measuring DC current as well. So let's get to it. These are all the equations you need to estimate how much power you can get out of your solar panel. I'm using here a Windy Nation 100-watt solar panel with a short circuit under standard test conditions current, a short circuit current of 5.94, we'll call it 6 for the fun of it. And that's basically that number, and the 100 watts are the two numbers I need to know from the solar panel to calculate how much power it should put out. Well, this equation right here is what you'll use to calculate the power for where you're at, sun level you have, and all that other stuff. All right, I'm going to read this to you. Math is a language, and I'm going to read it to you as if it's a language. The power output is a function of the solar irradiance, watts per meter squared, and the temperature. The power at STC is 100 watts, and we need to know the cell temperature. And we got to find out what the actual solar insolation is, irradiance, sun energy, sun power, whatever you want to call it. We'll use this equation right here. The actual sun energy with the geometry and all the environmental factors concerned is proportional to the current or present short circuit current measurement divided by the short circuit current labeled on the STC, this blue number here, times 1,000 watts per meter squared. Okay, so that's where we get the G from. But it requires us to measure the short circuit current. And that's what the multimeter is for. And the temperature. There's one piece of data that's not on this back label, and I had to go to the data sheet to get, and that's KP, the power temperature coefficient for my solar panel. By the way, these are pretty nice little solar panels. There are better ones out there, and there's others that are very, very similar. But these are very nice solar panels. All right, so KP, temperature measurement coefficient. I've seen it range from 0.3 to 0.5. My manufacturer's data sheet said minus 0.5%, and those are minus signs there. And what that minus sign kind of indicates is the hotter it gets, the less power you're going to get out. And that should be percent over temperature in degrees Celsius or Kelvin. Doesn't matter. The reference temperature for ITC is 25 degrees C. The reference irradiance for the standard test condition is 1,000 watts per meter squared. And what we're going to do is we are going to always do a temperature correction first, and then we're going to correct or adjust for the real life solar radiation irradiance that is occurring right now. So between these two equations here, I can get a good calculation or estimate of the power output given my environment. Okay, couple other facts of note. A MPP charge controller will harvest close to the max power from the above equation. A PWM charge controller will harvest the ISC measured times the battery voltage. They do not work at the max power point of the solar panel. Okay, let's go here and... All right, here's some basic assumptions that we have to have in our back of our brains to figure out things. The standard test conditions are a method to compare solar panels without environmental effects. Basically, they're going to give you operating parameters, the current, the voltage, the power, when you have 1,000 watts per meter squared shining on the panel, and the panel temperature is 25 degrees C. Well, I don't know about you, but where I live, the solar irradiation could be a whole lot less than that, and the temperature of the panel could get a whole lot colder. The method you always use to calculate the real output of the solar panel is you adjust for the temperature first, then you adjust or correct for the solar irradiance. MPPT charge controllers are power chargers. PWM charge controllers are current chargers. So when you look at an MPP, if you got 100, let's say you got 80 watts per coming out of your solar panel, it's going to put close to 80 watts into your battery. A PWM charger is going to put whatever the short circuit current is times your battery voltage into your battery. Another thing we have to consider, batteries are an infinite load sink compared to solar panels being a limited current source. And pulls down, and the battery pulls down the solar panel voltage to the battery voltage when using a PWM charge controller. PWM charge controllers operate below the maximum power point of the solar panel. The STC temperature is close to air temperature near freezing, 0 degrees C. And it's also close to a factory floor temperature of 25 degrees C at the same time. And that's because when you put a solar panel out in the sun, it heats up. And if the air temperature is at 0, it's going to heat up to close to 25 degrees C. And the factory floor temperature being 25 degrees, that's human workable. And they only shine the panel for a fraction of a second, so there's no heating of the panel. Some other considerations, I am going to assume the effects of temperature on the short circuit current is small enough to be ignored. And that's because the temperature coefficient for short circuit current is 0.06% or less. The panel temperature is equal to the individual cell temperature, and the solar panel is at thermal equilibrium, meaning the sun's been shining for a while and the panel had a chance to warm up. Solar noon, plus or minus a couple hours, is the best time of day to make a solar irradiance measurement because of a lower change in solar energy compared to mornings and evenings. I'm also assuming there are no shadows from clouds, trees, or buildings, and a clear line of sight between the sun and the solar panel can be established. Haze from water vapor is a real environmental factor, except maybe in a desert where the air is much drier. Sun to panel geometry is a factor in panel performance. This is why 2-axis trackers are used in solar farms. The normal or perpendicular sun rays are the effective value on the panel. All right. Off-angle sun rays can always be decomposed into a lateral and a perpendicular component, and only the perpendicular component is effective in making the solar panel work. And there's a slight tolerance there, because if you're off a degree or two, you won't notice it. All right, and here's the overdriving. Everything you do, every calculation you make, the power goes down at high temperature. Power goes up at low temperature. That's just for temperature. If the solar irradiance goes down, it can overwhelm the temperature effect. Okay, let's see. Slide. Now, this is kind of a preview slide. What I've done is I took my STC values and I created a IV curve from those STC values. Used Excel curve fitting using the exponential trend line, and I solved for the various parameters you need for a solar cell model. The power and the current look okay. I'm a little concerned that the method I'm describing above for calculating the open circuit voltage may be off a little bit. I'm still working on this, but this gives me a nice picture to work from. This curve is your power curve. This is your current versus voltage on my solar panel. The open circuit voltage is 22 volts, and the orange line here. This part of the curve where it goes from flat line basically to change of slope, that's the diode exponential nonlinear region, and I will often call that the knee of the curve. Anytime there's a slope change, I'll call that the knee of a curve, no matter what kind of device I'm talking about. And I don't know how to edit that out, excuse me. I'm new to this video making stuff, so you have to excuse me. Now, the MPPT charge controller works at the max power point, since this is a power curve. And that looks like for STC conditions. And that should come out to 100 watts output. The yellow curve is basically my STC curve. This is ISC equals 6 amps and V equals 0, and this is open circuit voltage, V equal 22, and the current equals 0. And the max power point is here at 100 watts. When designing anything, you want to work in what's called the linear region, where the curve is flat and slowly changing. Really, really want to avoid working at the actual max power point. Real MPP charge controllers will operate probably about here because that's a nice straight line for the power curve. This curve is at a higher input power. I think it's at 1100 watts per meter squared. Or is that, yep, that's higher than that one, so that definitely is the 1100 watts per meter squared input irradiance. And I've set the solar panel temperature to 40 degrees C, which is 104 degrees F. And the max power point is right here under those working conditions. Now, I haven't drawn a max power curve yet for the cold case, but my cold case is minus 10 degrees C, and the max power point is going to occur about here, and we can see that we're probably down around, let's call it 47 watts. Now, this is the area that a pulse width modulated charge controller works at. Basically, it starts working, assuming a drained battery, somewhere around 11 volts and keeps working until the battery is fully charged. It applies a short between the solar panel and the battery. So this changes, and it's basically fairly linear. The steps here, that's 1,000 watts per meter squared, that's 750 watts per meter squared, that's 500 watts per meter squared, and 250 watts per meter squared. Now, why do I have different values of irradiation? Well, the sun energy changes between winter and summer. The sun energy changes throughout the day. So you don't get a single level of power out of a solar panel. Depends on how bright the sun is, time of day, time of year, how much stuff is in the air between the sun and your solar panel, water vapor, gases, and things like that, dust, and just all the other gases up there that really don't do a whole lot as far as diminishing the amount of solar radiation you got, but it scatters it, so effectively diminishes it. Let's see. This MPP charge controller, like I said, that's where you're operating at. So if I compare that power point to that power point, you can see you pick up a whole lot of energy that you can harvest with an MPPT charge controller compared to a PWM. Now, if you look at this point to that point, you don't have a big difference between max power point and, I got to make sure I get this right. Which curve is that? This curve, the gray curve, which is here. Matter of fact, that almost says that you could get more power. Well, you get a constant current times the voltage. Let's say you got 6 times 12. That's, what's 6 times 12? 60, 72? 72 watts. And right here I'm saying I'm getting, looks like about 82 watts. All right. So I just threw a whole lot of information at you, and I do realize this is an eye chart, but it tells you a lot of information. And I derived these charts from just 3 data points: short circuit current, open circuit voltage, and the max power point for the panel at STC. All right, let's go on to the next graph. Now, let's say you want to guess what the energy that you can harvest is in another time of year. Like this is for the spring equinox, Cedar City, Utah. And we got 3 curves here. This is from the Measurement and Instrumentation Lab put out by our government in USA. And we have 3 measurements here. We have direct, normal. This is basically a sun tracker. This instrument for measuring the solar irradiance is always pointing at the sun. And this is basically this jump here. I'm going to call that's where the sun tracker acquired the target, the big old ball of sun. And this is 7 o'clock in the morning. This date is near the spring equinox. So the time here on this chart is in Mountain Standard Time. And solar noon occurs at this max point here, and it is not 12 standard time. It's off by about 45 minutes. This chart is if you took a solar panel and you laid it on the ground or a flat roof of an RV. This is how much power you can expect to get out. And this funky little blue line down here, that is what's called horizontal diffusion, and physicists will actually call that Rayleigh scattering of the sun. Okay? And I'm going to go back to the difference between horizontal and tracking is you have a geometry issue, because if you have a horizontal, you're not tracking the sun, but the sun has a certain elevation, maximum at noon, and lowest in the morning and in the evening. And it travels east to west across your panel. Okay, I think that's done. Oh, shut up. All right. Just blew off my dad. All right. Here's my little thing to measure my temperature. And this is a hot example. Take my 100-watt panel at STC. I'm assuming an air temperature of 40 degrees C, 104 degrees F, and a solar irradiance of about 1,000 watts per meter squared. I'm doing this for my area. I think this is peak for around the summer solstice on the east coast of the United States. I'm going to estimate the cell temperature using the knock method. And if we recall on the very first slide, there was a nominal operating temperature of 48 degrees on the label. And we use this is the air temperature, the nominal operating temperature. And for some reason, the knock method uses a reference temperature of 800 watts per meter squared. So I would expect the solar panel to get up to 75 degrees C. Now, I'm not real sure how accurate this knock method is, but it's a good guess. And if we add 30 to that, we get up to 70, so we're within a few degrees. Here I'm just plugging in the numbers, Kp of minus 0.5. Now that's percent, So I have to divide by 100. And this is the cell temperature minus 25, which is the standard temperature for STC. And since I'm using a energy irradiance on my panel at 1,000, divided by the reference wattage, 1,000, that equals 1. But this is saying that I'm going to only get 75 watts out of my panel when it gets this hot and I have this much energy. It's a 25% loss just due to the temperature. Since G, the energy I measured by measuring the short circuit current, is equal to G, the standard test condition of 1,000 watts per meter. The percent sign divided by 100, that just takes a percent number and turns it into a real number you can put into a spreadsheet or calculator. Understanding how the panel works will aid you in understanding how much power you can actually harvest. Calculation of cold. Now, this is an interesting one. I'm using minus 10 degrees C, which is 14 degrees F. This occurs in my state about once every 10 years. I never really calculated duration. I wonder if it's 11, which would be equivalent to a sunspot cycle. Once again, I'm using a temperature coefficient of minus 0.5%. I have a Pmax of 100 watts from STC, a nominal operating temperature of 48 degrees, and my reference temperature is 25 degrees C. And I'm going to assume, because I looked at some charts, that around the winter solstice, my irradiance is half that of what I get in the summer. I'm not going to walk through the math on this. I'm hoping you guys are taking screenshots everywhere, and I am assuming that you can walk through these equations. I'm correcting for the percent gain or loss due to temperature, multiplying by the label of the power output, and then taking the ratio of the expected irradiance at the winter solstice divided by the reference irradiance on the STC label. Now what's interesting, I get a 9% gain due to temperature, but because the irradiance is half of what it is in the summer, I'm only going to harvest 54.4 watts out of the solar panel. Okay, what I'm going to show you in this graph is how to measure the short circuit current. Oh boy, let's see. Start there. And I wish I knew what I was doing in video recording. All right, this is just a $5 multimeter I was able to get years ago. Notice I'm using the 10 amp DC input and just plug these probes directly into the MC4 connectors, and you can measure and set your dial to DC amps, and you can get the short circuit current with this. Just be careful that you don't do 2 panels at a time, because that exceeds the limit of 10 amp input for this device and you'll blow it up, and I did that myself. So don't measure 2 panels in parallel. This device is a DC clamp meter for measuring AC. Cost me about 40 bucks. Short the panel together by plugging the MC4 connectors together. Set the DC. The amp range for this device is 200 amps, so you shouldn't have a problem with that. Sometimes you just want to add a shorting wire between stuff 1 and into each MC4 connector and use that instead of plugging them together. Disconnecting MC4 connectors can be hard sometimes. Clamp your meter around the wire. Hit test. and you get your short circuit current. Okay, so we're